Welcome to this presentation on high-level design or HLD. Today we will explore its significance, role in software development, and key concepts that make HLD an integral part of system architecture. Let's dive in. Here's the agenda for our discussion. First, we will define high-level design and understand its importance. Then we will compare HLD with low-level design to see how they complement each other. We will discuss the role of HLD in the software development lifecycle or SDLC. Finally, we will explore some common use cases where HLD is applied. Let's begin by defining high-level design. High-level design or HLD is the process of outlining the architecture of a system and its major components. It focuses on defining the relationships between these components at an abstract level. HLD ensures that we have a clear vision of the system before diving into implementation details. HLD plays a crucial role in the software development process. It provides a clear vision for stakeholders to understand the system. It aligns system design with business requirements, ensuring the solution meets its objectives. HLD serves as a blueprint for the detailed low-level design phase. Lastly, it helps identify and mitigate potential risk early in the process. High-level design and low-level design are complementary processes. HLD focuses on the system's overall structure, interactions, and architecture at a broad level. In contrast, LLD dives deeper into the internal workings and implementation of individual components. Think of HLD as the architect's blueprint, while LLD is the engineer's detailed plan. Here's a side-by-side comparison of HLD and LLD. HLD focuses on system architecture, while LLD is concerned with component level details. HLD provides an abstract overview, whereas LLD offers a concrete and detailed view. These distinctions are critical for efficient and scalable system design. HLD in software development. In the SDLC, HLD follows requirement analysis and precedes low-level design. It acts as a bridge, translating business requirements into technical architecture. The typical process flow starts with requirement analysis, followed by HLD, LLD, implementation, testing, and finally deployment. Why is HLD so important in the SDLC? Well, it defines the system's architecture and lays the foundation for development. It serves as a roadmap, ensuring the development team has clear guidance. HLD prevents misalignment by ensuring the system design aligns with the business needs. HLD is applied in a variety of scenarios, including designing system architecture for large-scale applications, developing software products with multiple interacting components, migrating legacy systems to modern platforms, creating cloud computing systems, or designing APIs. These use cases highlight the versatility of HLD. Let's take an online shopping system as an example. In the HLD phase, we identify key components such as the user interface for customer interactions, inventory management for tracking stock, payment gateways for secure transactions, and shipping services to handle order deliveries. The focus is on defining how these components interact rather than dividing into their implementation details. In conclusion, high-level design is essential for setting the direction of the software development process. It defines the overall structure of the system, acting as a bridge between business requirements and detailed design. By focusing on the big picture, HLD ensures the system is scalable, maintainable, and aligned with business goals. That's that wraps up our discussion on high-level design. Do you have any questions? Thank you for your time and attention. Welcome to the session on Principles of Good High-Level Design, also known as HLD. In today's session, we will take a deep dive into the key principles that form the foundation of effective system design. Let's get started. High-level design is a critical phase in software development. In this session, we will explore key principles such as modularity, abstraction, loose coupling, high cohesion, scalability, performance, and maintainability. These principles help ensure that a system is robust, flexible, and easy to maintain. Modularity is the concept of dividing a system into smaller, manageable components where each module performs a specific function. This principle simplifies the design process, promotes reusability, and makes maintenance more efficient. Why is modularity important? First, it separates concerns, allowing developers to focus on individual functionalities. Second, it promotes reusability by enabling the use of existing modules in new systems. Third, modularity enhances maintainability, making it easier to update or fix a module without impacting the entire system. Lastly, it supports independent testing of components. Let's take the example of an e-commerce application. It consists of several modules like product catalog, shopping cart, order management, and payment gateway. Each module has a specific responsibility, which makes development, testing, and scaling much easier. Abstraction and encapsulation are closely related principles. Abstraction hides complex implementation details and provides a simplified interface, while encapsulation ensures that data and methods are bundled together, restricting unauthorized access to internal details. Abstraction simplifies complex systems by hiding unnecessary details and focusing on functionality. Encapsulation, on the other hand, protects data by restricting access to internal elements through methods. This combination ensures security and clarity in system design. Consider a banking system. A user interacts with a bank account class through methods like deposit and withdraw, which represent abstraction. Meanwhile, the account balance is a private attribute that can only be modified through these methods, representing encapsulation. Loose coupling and high cohesion are essential for creating systems that are easy to maintain and extend. Loose coupling minimizes dependencies between modules, while high cohesion ensures that each module focuses on a single responsibility or set of related tasks. Loose coupling allows for flexibility in design. Changes in one module are less likely to impact others. It also ensures extensibility, enabling developers to add new features or replace components without breaking the system. High cohesion makes modules easier to understand and maintain. It also reduces redundancy and keeps responsibilities focused. For example, a shopping cart module should only manage items in the cart without dealing with payment or shipping. Here's an example. A loosely coupled system might consist of independent services for user authentication, product management, and other processing and order processing. High cohesion ensures that the payment processing module focuses solely on payment tasks, avoiding unnecessary dependencies. Scalability, performance, and maintainability are critical for long-term success. Scalability is about handling increasing loads. Performance focuses on systems efficiency, and maintainability ensures the ease of updates and modifications. Scalability can be achieved through horizontal scaling, which adds more machines, or vertical scaling, which increases the capacity of existing resources. Cloud computing platforms like AWS and Azure offer elastic scaling options for modern systems. Performance can be improved by optimizing algorithms, caching frequently used data, using load balancers to distribute traffic, and employing CDNs to deliver content faster. These strategies ensure a seamless user experience. To enhance maintainability, write clear and concise code, design modular components, maintain comprehensive documentation, and implement automated testing. These practices make it easier to update and manage the system over time. For example, a video streaming service might use horizontal scaling to support millions of users. A search engine could optimize query responses using caching. A CMS with modular design and clear documentation ensures easy updates and maintenance. In summary, the principles of good HLD, modularity, abstraction, loose coupling, high cohesion, scalability, performance, and maintainability laid a foundation for effective system design. Applying these principles lead to robust and flexible systems. This concludes our session on principles of good HLD. If you have any questions, feel free to ask now. Thank you for your time. Welcome to this presentation on basic design patterns in high-level design. Today we will explore the foundational concepts of design patterns, their purpose, and how they contribute to high-level design. Let's get started. Design patterns are reusable solutions to common problems in software design. They serve as templates to address recurring challenges in development. These patterns fall into three main categories: creational, structural, and behavioral. Understanding and applying design patterns helps streamline the design process while improving system quality. Why are design patterns important? First, they offer standardized solutions, making it easier to address common problems. Second, they improve system modularity and scalability, simplifying maintenance and upgrades. However, overusing patterns can lead to unnecessary complexity. It's essential to apply them thoughtfully. Creational design patterns focus on object creation mechanisms. They help ensure objects are created in a controlled and flexible manner. Key examples include the singleton and factory patterns. These patterns are especially useful when we need to dynamically create objects or limit instantiation. Structural design patterns emphasize the composition of objects and their relationships. They ensure that large structures are well organized and maintainable. Examples include the adapter, composite, and decorator patterns. These patterns are commonly used when managing complex relationships between objects. Behavioral design patterns deal with communication and interaction between objects. They allow for flexible and dynamic behavior within a system. The observer and strategy patterns are excellent examples, enabling systems to adapt to changing requirements in real time. The singleton pattern ensures a class has only one instance while providing a global point of access. It's particularly useful for managing resources like database connections or logging services, where multiple instances could lead to issues. The singleton pattern relies on three key components: a private static instance, a public method to access the instance, and a private constructor to restrict direct instantiation. These elements ensure that only one instance of the class exists throughout the application. Imagine a database connection manager. With a singleton, we avoid multiple connections being created unnecessarily. This not only optimizes resource usage but also ensures consistency. However, global access can make testing more complex. The factory pattern provides a way to create objects without exposing the instantiation logic. It's ideal for scenarios like creating different types of users or payment processors, where the exact type of object isn't known upfront. The factory pattern involves a method that returns different product types along with an abstract class or interface defining the products. This design promotes flexibility and decouples the client from specific implementations. Consider a payment gateway system. The factory pattern allows the system to dynamically create payment processors such as credit card or PayPal handlers. This approach ensures scalability while maintaining clean code structure. The observer pattern establishes a one-to-many dependency between objects. It's widely used in real-time systems such as stock price trackers or event-driven applications, where changes in one object should trigger updates in others. An observer pattern consists of a subject which is observed and observers that need updates when the subject changes. This structure promotes loose coupling, making it easier to extend and modify the system. A great example is a weather monitoring system. When weather data changes, it updates multiple devices like mobile apps and websites. The pattern ensures efficient communication between the subject and its observers. The strategy pattern defines a family of algorithms and lets the system choose one at runtime. It's perfect for scenarios like switching between sorting algorithms or applying different pricing strategies in an e-commerce platform. The strategy pattern consists of three main objectives: the context, which uses the strategy interface, and concrete strategies, which implement specific algorithms. This design promotes flexibility and reusability. An e-commerce platform can use the strategy pattern to apply different discount algorithms such as percentage based discounts or buy one get one free offers. The pattern makes it easy to add or modify strategies without affecting the rest of the system. Design patterns in high-level design are valuable for scalability, maintainability, and performance optimization. For instance, the singleton pattern helps manage resources efficiently, while the factory and strategy patterns allow for dynamic behavior and flexibility. In summary, design patterns provide standardized solutions to recurring challenges. By leveraging patterns like singleton, factory, observer, and strategy, we can design systems that are scalable, maintainable, and flexible. Proper application of these patterns is key to creating robust software. Thank you for your attention. I hope this presentation provided valuable insights into design patterns in high-level design. Now I would be happy to answer any questions you might have. Welcome everyone to today's session on understanding software architecture. This is day 4 of our series on high-level design where we will dive deep into the concepts of software architecture, its types, and its practical applications. Let's get started. Today, our goal is to build a foundational understanding of software architecture. We will explore the distinction between architecture and design, different types of software architectures, and how to make informed architectural decisions. By the end of this session, we will also see some real-world applications and understand the trade-offs involved in architectural choices. Let's begin by clarifying the difference between software architecture and software design. Architecture focuses on the high-level structure of a system, defining its components and their interactions, while addressing non-functional requirements like scalability and security. On the other hand, design deals with the internal details of individual components, including algorithms and data structures. To summarize the distinction, architecture concerns the overall system, its scalability, and fault tolerance, while design focuses on implementing the functionality of individual components. Both are critical, but they operate at different levels of abstraction. Software architectures can be broadly classified into different types, such as monolithic, microservices, and layer architectures. Each type has unique features and use cases, which we will explore in the following slides. In a monolithic architecture, all components are tightly bundled into a single application. While this approach simplifies development and deployment for small applications, it becomes difficult to scale and manage as the system grows, leading to tight coupling and a reduced flexibility. Microservices architecture divides the system into small, independently deployable services. This offers advantages like independent scaling and fault tolerance, making it ideal for large, complex systems. However, it introduces challenges like communication overhead and service management complexity. Layered architecture organizes the system into distinct layers such as presentation, business logic, and data access. This separation of concerns improves maintainability and testability but may introduce performance overhead in some scenarios. Client-server architecture is a model where clients request resources or services and servers respond to these requests. It's scalable with distributed servers but can face challenges like server overloading and security concerns in data transmission. In event-driven architecture, systems react to events triggered by user actions or system changes. This approach enhances responsiveness and scalability while promoting loose coupling between components. However, managing events and ensuring traceability can be complex. Choosing the right architecture depends on several factors such as scalability, performance, maintainability, and cost. Additionally, the specific needs of the system and its users play a critical role in guiding these decisions. Every architectural design involves trade-offs. For instance, while microservices offer scalability, they add complexity. Similarly, layer architecture enhances modularity. It can introduce latency. Understanding these trade-offs is crucial for effective decision making. Here are some real-world examples. Traditional enterprise applications often use monolithic architectures, while companies like Netflix and Amazon leverage microservices for scalability. Layered architecture is common in banking systems and enterprise applications. To recap, software architecture defines the overall structure and interactions within a system, addressing high-level concerns like scalability and security. Design, on the other hand, focuses on implementation details. It's essential to choose the right architecture based on our system's specific needs. This concludes today's session on software architecture. If you have any questions or need further clarification, feel free to ask. Let's open the floor for discussion. Welcome to day 5 of the high level design course, Software Requirements and System Understanding. Today we will dive into the crucial steps of collecting, analyzing, and translating requirements into actionable system designs. In today's session, we will explore the following topics: collecting and analyzing requirements, translating business requirements into technical ones, defining the system context, creating a functional decomposition, establishing a preliminary system architecture, and in iterative refinement leading to final system specifications. Let's begin with the basics. What are software requirements? Requirements can be categorized into functional requirements, which specify the system's features or tasks, and non-functional requirements, which define how the system should perform, such as its speed, scalability, or reliability. To collect and analyze requirements effectively, stakeholder engagement is key. Methods such as interviews, surveys, and workshops allow us to gather diverse perspectives. Each approach offers unique advantages for understanding user needs and expectations. Functional requirements describe the specific tasks or actions a system must perform. For instance, allowing users to log in is a functional requirement. Non-functional requirements, on the other hand, focus on performance and constraints, such as the system should handle 1000 concurrent users. Both, both are critical for robust design. Eliciting requirements often involve tools like use cases, which detail system interactions, and user stories, which provide concise descriptions of functionality. Prototypes and mockups can also help, by offering visual representation that stakeholders can evaluate. Once requirements are gathered, validation is essential. This involves engaging stakeholders to confirm the requirements meets their expectations. Techniques like traceability metrics can help link requirements to specific test cases. Additionally, prioritizing frameworks like Moscow, must have, should have, could have, and won't have help manage scope efficiently. Business requirements describe the problem, while technical requirements provide the solution. For example, a business requirement might state customers need faster checkouts, and its technical counterpart might specify implement a one-click payment system. Business rules such as defining pricing discounts or eligibility criteria must be translated into system logic. Similarly, constraints like budget or time limits need to be incorporated into the design to ensure feasibility. Mapping functional requirements involves breaking down high-level functionalities into technical components. For example, the requirement support multiple users translates into a technical solution like multi-user authentication. This ensures alignment between requirements and system design. Choosing the right technology is crucial. For instance, using Spring Boot for backend development and React for frontend can streamline the development process. The right tools ensure the system is both efficient and maintainable. Non-functional requirements often dictate system performance and security. For example, to meet the requirement, system should respond within 2 seconds. We might implement database optimizations or caching strategies. Security requirements like data encryption guide decisions about authentication protocols. Scalability and maintainability are critical for system longevity. Scalability ensures the system can handle increased demand through horizontal or vertical scaling. Maintainability focuses on creating modular, clean, and extensible code for easier updates. Defining the system context means understanding its boundaries, what's in it in scope and what's out. This includes identifying external systems that the software will interact with and how those interactions will be managed. By defining boundaries, we determine what data will be processed within the system and what might be outsourced, such as payment processing. Additionally, we establish protocols for external communication like REST APIs or SOAP. Functional decomposition involves breaking the system into smaller, manageable modules. For example, an e-commerce system might have separate modules for user authentication, inventory management, and payment processing. Mapping data to use cases involves detailing the inputs and outputs for each system module. For instance, the authentication module might accept user credentials as input and return authentication results as output. Next, we establish a preliminary system architecture. This includes outlining key components and deciding on the architecture type. whether it's monolithic, microservices based, or service oriented. Design is rarely perfect in the first iteration. Iterative refinement allows us to incorporate feedback, improve prototypes, and adapt designs to changing requirements. Regular reviews ensure that design stays aligned with stakeholder needs. Finally, we consolidate everything into formal system specifications. This includes reviewing functional and non-functional requirements and documenting technical specifications in the form of an SRS, Software Requirements Specification. That concludes today's session on software requirements and system understanding. Remember, gathering and translating requirements is the foundation of a successful high-level design. Thank you for your attention. Welcome to day 6 of our high-level design course. Today we will be diving into diagrams in HLD, specifically focusing on UML diagrams. These visual representations are crucial in software design, and we will explore how they help in building a strong architectural foundation. Let's get started. UML or Unified Modeling Language is a standardized modeling language used to visualize, specify, construct, and document software systems. It serves as a bridge between technical teams and stakeholders, providing a common ground for communicating complex system designs. UML helps document both static and dynamic aspects of a system, ensuring that the design process is understood by everyone involved. Why is UML so essential in software design? Well, it enables teams to communicate effectively about the system structure and behavior. UML helps in defining the system's architecture clearly, supporting different stages of the software development lifecycle, particularly high-level and low-level design. It makes it easier for stakeholders to understand how the system works, ensuring everyone is on the same page. UML diagrams can be broadly classified into two categories: structural diagrams and behavioral diagrams. Structural diagrams focus on the static structure of the system, such as class diagrams and component diagrams. Behavioral diagrams, on the other hand, represent the dynamic interaction and processes like sequence diagrams and activity diagrams. Both types are essential in HLD, helping to convey different aspects of the system. Let's start with the class diagram. This is one of the most commonly used UML diagrams in high-level design. It represents the static structure of the system by showing classes, attributes, methods, and relationships. The purpose of the class diagram is to define how different entities in the system are related. For example, we might have classes such as user, product, and order in an e-commerce system with relationships showing how these entities interact. Here's an example of a class diagram for an e-commerce system. We have several classes: user, order, product, and payment. The user class might have attributes like name and email, while the order class would include attributes like order ID and order date. Relationships between these classes show that a user can place an order can contain multiple products, and payment is processed for each order. Next, let's look at the sequence diagram. A sequence diagram shows how objects interact in a particular sequence of events over time. It's perfect for showing the flow of messages between objects. For example, in an online payment process, a user sends a payment request to the payment gateway, which then communicates with the bank to process the payment and confirm the transaction. In this sequence diagram example, we see how the user, payment gateway, bank, and transaction interact during a payment process. First, the user initiates a payment which is processed by the payment gateway. The bank confirms the transaction and the transaction object updates the order status. Each step is shown in sequence, allowing us to visualize the entire flow of operations. Moving on to the component diagrams, these diagrams are used to represent the major components of a system and their relationships. They show how different parts of the system depend on each other. For example, in a microservices architecture, components like user service, payment service, and inventory service might communicate with each other, each with its own responsibility and set of interfaces. In this component diagram example, we see the interaction between different services in a microservices architecture. The user service, payment service, inventory service, and notification service components each perform specific tasks, and we see how they depend on each other through interfaces and dependencies. This type of diagram helps us understand how the overall system is structured. Creating UML diagrams for high-level design involves a few key steps. First, gather requirements from stakeholders to understand the business logic. Next, identify the major components of the system. Once we know what we need to model, choose the appropriate UML diagram for each aspect. Then map out the relationships between components and refine your diagrams to ensure clarity and precision. Now, let's put this into practice. Imagine we need to design UML diagrams for a library management system. We start by creating a class diagram to represent entities like book, member, loan, and staff. Next, we create a sequence diagram to show the process when a member borrows a book. Finally, we create a component diagram to show the major system components such as user interface, database, and loan management. Tools for creating UML diagrams. So to create UML diagrams, we will need the right tools. Popular options include Lucidchart, Microsoft Visio, and Draw.io. Lucidchart is great for cloud-based collaboration. Visio is ideal for enterprise level diagramming, and Draw.io is free open source tool that that's perfect for smaller teams or individual use. Choosing the right tool depends on our needs. Lucidchart is great for teams working collaboratively in the cloud. Microsoft Visio is the go-to tool for businesses that require detailed and professional diagrams. For individuals or small teams, Draw.io offers a free, accessible option with many features. In conclusion, UML diagrams are essential for high-level design in software development. They provide clear, standardized ways to represent the structure and behavior of a system, helping teams communicate effectively. Mastering these diagrams, especially class, sequence, and component diagrams, will enhance your ability to document and communicate system designs. Thank you for your attention. Now, I would like to open the floor for any questions that you have. Feel free to ask about UML diagrams, how they are used in high-level design, or any other related topics. Let's discuss. Welcome to today's presentation on Tools for High-Level Design, or HLD. In this session, we will explore various tools that help in creating effective high-level design diagrams. Let's dive into how these tools can enhance the design and communication process. High-level design, or HLD, is an essential phase in software development. It involves visualizing the architecture, system components, and their interactions. Specialized tools are used to create diagrams that convey complex ideas clearly. In this presentation, we will look at popular tools for HLD, including Lucidchart, Microsoft Visio, Draw.io, and more. Why are these tools so important? First, they provide clarity by creating visual diagrams that are easy to understand. They also enable collaboration, allowing teams to provide feedback on designs. Furthermore, these tools serve as documentation, ensuring designs are saved for future reference. Additionally, using these tools can reduce errors early in the design process. Let's begin with Lucidchart, a cloud-based diagramming tool that's popular for team collaboration. Lucidchart allows a real-time collaboration on diagrams, which is great for teams working remotely or across different locations. It offers a wide range of templates for HLD, UML, and network diagrams and integrates seamlessly with Google Workspace, Microsoft Office, and Slack. Lucidchart is ideal for visualizing system architecture, including microservices and monolithic systems. It's also great for component interaction diagrams, such as sequence and component diagrams, and even for creating entity relationship diagrams for database designs. Real-time collaboration features make it easy to share and receive feedback even with remote teams. Next, we have Microsoft Visio, a widely used tool in enterprise environments. Visio is known for its extensive library of shapes and diagrams. It supports UML, flowcharts, and network diagrams and integrates well with other Microsoft Office tools. It also offers advanced customization options, which are perfect for enterprises requiring precise system modeling. Visio is especially useful for detailed architectural and system level designs. It's also used for creating network and infrastructure diagrams, visualizing servers, networks, and data flow. Visio is commonly used to represent HLDs to stakeholders, such as during board meetings or client presentations. Let's now look at Draw.io, a free open source diagramming tool. It's a browser based application with offline desktop support. Draw.io doesn't require an account to start creating diagrams, making it perfect for quick, simple HLD creation. It integrates with cloud services like Google Drive and GitHub, which makes it ideal for collaborative work. Draw.io is great for quickly creating simple HLD diagrams. Its interface is user friendly, making it ideal for live projects. It's perfect for teams who need a free and accessible tool for basic HLD creation and collaboration through cloud storage like Google Drive. Enterprise Architect is a comprehensive modeling tool used for large-scale systems. It provides full UML support and integrates with other modeling languages like SysML. It's designed for rigorous modeling with advanced version control and detailed documentation generation, making it perfect for large enterprises with complex systems. Enterprise Architect is used for complex system modeling where precise specifications are critical. It's also helpful for generating detailed reports for compliance and regulatory purposes. Additionally, it supports multiple modeling standards like SysML, UML, and BPNP, making it versatile for various industries. Creately is a visual collaboration tool that allows teams to work together on system designs in real time. It offers pre-built templates for HLD and UML diagrams, and its easy sharing and export options like PDF and PNG make it ideal for teams collaborating on design design work remotely. Creately is perfect for collaborative design, especially for teams working remotely. It's used for creating flowcharts, UML diagrams, and HLD breakdowns. It also helps in prototyping ideas and systems for iterative feedback, making it easy to visualize and adjust designs. Plasmic mockups is primarily a wireframing tool, but it can be useful for simplified HLD diagrams. Its drag and drop interface allows for quick wireframing and system design. It's especially useful during brainstorming sessions and for early age design with its hand drawn style. Plasmic is ideal for rapid prototyping and brainstorming, especially in the early stages of a project. While it's more commonly used for UI design, it can also be used to create low fidelity high level diagrams, allowing teams to quickly sketch out system components and ideas for discussion. Here's a comparison of the tools we have covered. Each tool has its unique feature and strengths. For example, Lucid Chart excels in real-time collaboration, while Visio offers advanced customization for enterprise-level design. Draw.io is free and accessible, and Enterprise Architect is perfect for large, complex systems. Creately provides visual collaboration, and Plasmic is best for rapid prototyping. To summarize, the choice of tool for high-level design depends on the size of your project, its complexity, and the level of collaboration needed. Whether we need detailed diagrams for enterprise use or simple prototypes for brainstorming, the right tool can significantly improve how we visualize and communicate our system design. That concludes the presentation on tools for high-level design. I would now like to open the floor for any questions or further discussion. Feel free to ask about any of the tools we have discussed or how they can be applied in your own projects.